Rick Kenyon from Yale, who's going to talk about higher rank dimers.
Thanks. Yeah, thanks, and happy birthday, Philippe. I was trying to remember when we first met, but I don't know, 20 years or so. And you know, I've always been very impressed with Philippe's work, and I've looked up to him, and he's always seems to be, you know, light years ahead of what I'm interested in and doing, but always trying to catch up. But you know, always enjoy our conversations, and always happy to learn what he's doing and have discussions with him. I want to talk about higher rank dimers. This is going to be based on joint work with Dan Douglas, who's in Virginia. Nick Ovenhouse is a postdoc at Yale. Hao-Lin Shi is my grad student. David Wilson, some work from many years ago with David. And you know, I've been working on a dimer model for a long time, and maybe many of you, know about dimers. It's sort of percolated through lots of our common interests. And recently, I've been, talking about. I did some work with Sasha Goncharov, and he got me thinking about dimers from a slightly different point of view, and in particular. Putting some non-commutative weights on, and particular matrix weights, led to this. We realized that the whole theory of dimers can be generalized in a certain way to higher rank, and that's what I want to talk about today. Here's a small sort of motivational slide. This was for other probabilists, so maybe it's not new to people here, but if I take two dimer covers and just superimpose them, I took a blue dimer cover of the square and a red one of the square minus the four corners. So the red dimer cover does not cover the four corners, but you draw them on top of each other, and then of course you get these chains where you get loops and some doubled edges, and these chains which connect the four corners. And you can ask, well, there's two possible ways they can connect. A can connect to B and C to D, or they can go B to C and A to D. And you can ask what the probability of those two different events are. You just take two independent uniform random dimer covers, superimpose them. What's the probability that the connection goes one way versus the other way? And of course, if it's a square, the probabilities are 50-50, just by symmetry. But if you have a more complicated domain like this, peanut-shaped domain in the complex in the z-squared lattice, and I take the lattice spacing epsilon tending to 0, then this probability converges as epsilon goes to 0 to some non-trivial number, some interesting number, which, well, one can prove that with appropriate boundary conditions, this number converges, and it just is basically the cross ratio, the cross ratio of A, B, C, D when you map them to the upper half plane. So this is not a very difficult calculation to do, but it does indicate that there's some sort of conformal invariance in the dimer model, and this was the start of a long story of connecting the dimer models to conformal invariant and conformal field theory. Feel free to interrupt with questions if you, does everybody know what the dimer model is? Yeah, okay. On the other hand, if I tried to do the same experiment with 3 dimer covers, I just took a red, green, and a blue, and I drew them on top of each other, you don't see anything. There doesn't seem to be any internal structure. It's hard to see the system kind of percolates, and you don't really see any large-scale internal structure. And the goal of this talk is to explain that there is some internal structure there and show you how to find it. We're going to be more general than just 3 dimers. I'm going to talk about these things called multi-webs, and there's one main theorem which I'm going to get to, and it'll require some explanation, and then there's some applications. So let's talk about a multi-webs, and so the underlying object for us is a planar bipartite graph here, and I want to now part of the data is a a multiplicity at each vertex, which is just a natural number, as indicated here. And those are going to be dimensions of some vector spaces. We assign each vector space some vector space of some dimension, which is allowed to vary from vertex to vertex. N sub v is the dimension of this vector space. Just think of it as Rn sub v. And then a quiver representation, or just a connection, let's just call it a connection. It's just a collection of maps, linear maps between the corresponding vector spaces. So for each edge, we have a linear map, which may be just a, if you just think, you can just think of it as a matrix of the appropriate dimensions. This is a map from a two-dimensional vector space to a three-dimensional vector space. Feel free to choose a basis for those vector space, then all the maps just become matrices.
You always consider maps from black to white.
Yeah, all the maps are always going from black to white. Thank you. And in the special case where all the multiplicities are the same, and the matrices are invertible, then you can call this a GLN connection or GLN local system, right? So this is a sort of a generalization of a GLN local system where the ends are allowed to vary and the maps don't have to be invertible. Now, so the objects which are going to generalize dimer covers are called multiwebs, N multiwebs. The boldface N means that N can vary from, N boldface is just a multi-index, so it's a function from vertices to integers, like, as indicated. So what's a multi-web? It's just a function on the edges which takes positive integer values and sums around each vertex. The sum of the multiplicities sum to the vertex multiplicity. And so for example, on the left, is there a pointer? Somebody took the pointer? I don't know where it went. Never mind. Je pense pas, non? Ah, here it is.
Okay.
Yeah, so here's an example of a multiweb in blue, right? You assign to each edge a non-negative integer, and the sum around each vertex has to add up to the multiplicity there. And you can think about this as just a function on the edges, or you can think of it as sort of a multi-graph like this. So you throw away the edges of multiplicity 0, and then you put a doubled edge here, and so on. That's a multiweb. And of course, yeah, if all the dimensions, if all the vertex multiplicities are 1, then a multiweb is just a dimer cover, because then you have to, the sum around each vertex has to be 1, so there's exactly one, each vertex participates in one edge. So it does generalize the dimer cover situation. Oh yeah, and so let's call omega n the set of multiwebs, and for it to be non-empty, there's one obvious condition, which is that the sum of the white multiplicities has to be equal to the sum of the black multiplicities if the graph is bipartite, which it will be for this talk. And there's also some inequalities you need to satisfy. And so here's the main theorem, which I want to talk about today. There's a certain function, natural function on multiwebs which we call the trace, which I will define in a minute. And then there's an analog of the Castellane determinant, K, in this setting, and it's in the Castellane matrix, and the determinant of that Castellane matrix is the sum of traces of multiwebs. And okay, so in this special case of dimer covers, when all the multiplicities are 1, then the trace is just 1, and so this is just a sum of dimer covers. It's the number of dimer covers, the determinant. But in the current case, this matrix will depend on all the linear algebra, all that connection stuff.
And it is truly a new theorem, so you cannot do that by a local decoration as some other theorems just happen.
Yes, you can. You're way ahead of me. But this point of view, has a lot more symmetry because as you have all these base, at each vertex there's a sort of, if you do an SLN base change at that vertex, the traces don't change, and so even though there is a scalar version, I mean I'm just talking about free fermions in the end. Somehow this viewpoint is much more not just compact, but shows a lot more symmetry than you would in the usual setting, in the scalar setting. Okay, so here's a couple very simple examples. Here's the 6-vertex model, or square ice model, which I think probably everybody here is familiar with. Here's a way to model it with this from this point of view. So I take the square grid and I put a vertex in the center of each edge, right? And then at each white vertex now, I'm going to have multiplicity 2, and at each black vertex I have multiplicity 1. Then what is a multi-web? Multi-web has to cover, it's a set of edges which covers each vertex, white vertex twice and each black vertex once. And so it looks exactly like a square ice model. So in that sense, the square ice model is a set of multi-webs. Each square ice configuration is a multi-web for these particular multiplicities. Okay, and once you've done that, then the 20-vertex model, which I did learn about from Philippe, is another example. You just do the same kind of story. You take the triangulation, you put a black vertex in the center of every edge with multiplicity 1, and the white vertices have multiplicity 3, and then each multi-web is a covering of this graph with these little trivalent molecules. And of course, now you can put all the matrices in here, and what you will find, the sort of Castellane determinant tells you about the free fermionic points of these models, which turn out to be what we might call determinantal tensor networks. Oops. Okay. What can you say about how do you count dimers? Well, this is just a reminder. If you have a planar bipartite graph, there's a certain matrix whose determinant here counts the number of dimer covers, and that matrix is related to it's very closely related to the adjacency matrix. You just take the adjacency matrix of the graph. Well, you take the sort of bipartite adjacency matrix whose rows are indexing the white vertices and columns indexing the black vertices, and then you get a plus or minus 1, you put in some signs. And what's the role that these signs play? Well, there's some condition on the signs. There are several ways to say this, but what you want is around every face, the number of minus signs is some function of the length, which is minus 1 to the L over 2 plus 1, which is telling you something. If you think of the point of this slide was to say that to get the Castellane matrix, you take the adjacency matrix and you put on top of it a certain connection, a plus or minus 1 valued connection on the edges, and the connection has a certain monodromy around each face. So this is I'm just introducing some terminology here to see that the original Castellane theorem with the assigned adjacency matrix can be thought of as just putting a certain kind of connection on the graph, a connection with a certain monodromy condition around each face. So that point of view helps in the more general setting, right? So here's our theorem again. I haven't told you what the trace is, but I have told you what the n multi-webs are. Let me tell you what the left-hand side is. What matrix do we put here? Well, we do this kind of naive thing. We on each edge we have a matrix, and we just make the adjacency matrix of the graph, but instead of scalars on the edges, we put those matrices on the edges. And again, we put the Castellane signs. We tensor with the Castellane connection. So, for example, if this is my graph, I've got it's a bipartite graph, and on each edge I've got some matrix. In this case, A is a matrix going from a two-dimensional vector space to a one-dimensional vector space, so it's a 1 by 2 matrix. The Castellani matrix is just this matrix of matrices, right? There's two rows here because there's two white vertices, and there's two columns because there's two black vertices, and A goes from black vertex 1 to white vertex 1. But then you do the sort of the only thing you can do, which is to replace each matrix here with its little block of entries. So here capital A is a 1 by 2 matrix, capital B is a 3 by 2 matrix, and so on. And when you sort of remove the parentheses, you get a block matrix. You get this matrix K tilde of scalars. The scalar matrix, and it's square because it's a square matrix as long as the sum of the black multiplicities equals the sum of the white multiplicities, and so it's something you can actually take the determinant of. And so that's this matrix K tilde, which goes on the left-hand side of the equation.
Question?
Sure.
Don't you have a way to reabsorb the sign of a Castellani connection into phi itself?
Yes, you can if you want.
Okay. But you don't do.
But then you'll get something else on the right-hand side. So in order to define because the trace is something that's not, we didn't come up with this trace. It's some sort of Reshatikin-Tareyev invariant for this model, and so if you try to absorb the signs into the matrices themselves, then the right-hand side will be a little bit different. Okay, so so now I have to tell you what the trace is. At least you know what the left-hand side is, and I have to tell you what the trace of a multi-web is. Okay, so remember what a multi-web is. It's some function on the edges of the graph, integer-valued function on the edges of the graph with the appropriate summation condition at each vertex. So let me first assume that all the edge multiplicities are 0 or 1. Then I'll tell you how to generalize in later. So if they're all 0 or 1, you can just throw out the edges of multiplicity 0 and just keep those of multiplicity 1. And around a vertex if this vertex has multiplicity n, there are n edges, E1 through En around that edge. And also sitting at that black vertex, there's a vector space of dimension n. And so what I'm going to do is put a copy of that vector space on each sort of, along each edge, one copy along each edge, V1, V2, and so on up to Vn. So now I've got n vector spaces, each of dimension n. And let's suppose they have some distinguished bases, E1 through En. And now I'm going to define I'm going to take the tensor product of those n vector spaces. So I've got a tensor product of n vector spaces, each of dimension n, and I'm going to define a particular vector in that tensor product called the codeterminant. So here's the definition. It's just it looks kind of like a determinant, except that the individual entries are each in a different vector space. So the codeterminant is a special element inside the tensor product of n vector spaces, each of dimension n, and it's defined like this: sum over the symmetric group, the signature. So this is the E. This is the sigma of 1th basis vector of the first vector space, and that's the sigma nth basis vector of the nth vector space. And you take this as sort of anti-symmetrizer. One special property of this vector that you can notice right away is that it is invariant under simultaneous SLN base change. If I do a change of basis or pre-multiply all these vector spaces by the same SLN matrix, then the codeterminant doesn't change. So it is, in some sense, a natural object. And okay, so we'll do the same thing at each vertex, including the white vertices. But in the white vertices, I want to think of the vector spaces at the white vertices as the dual vector spaces. And then the trace of my multi-web now is just obtained by some big tensor contraction. I take all the codeterminants at the black vertices, tensor them together. Then for each edge, right, each edge now corresponds to one of the tensor components in this big tensor product. I can apply the map, the connection along that edge to map it over into the white vector space, and then contract with the dual vector over here. So there's a lot going on here, but maybe it's not so important. It's a little bit hard to understand what's going on, but in any case, the trace of the final object, the trace is just a number, a scalar, which depends on all the matrices themselves, but only depends on the matrices and of course the edges involved here. Okay, it's a little bit hard to digest the first time you see it, but it's just some linear algebra.
Is there some special property of the trace as you define it that sort of makes it natural in this problem?
Well, yeah, this is the most important property, the SLN invariance. And the other property is that it's the right thing to put in the theorem, right? So in some sense, the theorem follows without much trouble once you have the correct definition. Yes?
Do you recover the usual trace by a special case of a linear operator?
Yeah. Yeah, why do we call this a trace? It doesn't look like a trace of any matrix. It's not the trace of any matrix, but I'll discuss that in a second, okay? Maybe it should be called something besides trace. But if somebody has a better terminology, it's a little bit late because, if you were paying close attention, you might worry about there was some, right, there's a little mark here. You have to, if n happens to be even, then there's an extra sign which depends on where you start, right? Because if I do a cyclic rotation here, I'll get an extra sign. So what you do is you put you have to upgrade the circular order at each vertex to a total order, linear order, and so you put a little mark there called the cilium at each vertex, which can be arbitrary. It just changes the sign of the trace at the end it just changes the sign of the trace. The sign of the trace will depend on the choice of linear order, but that's the only thing. That's why in the theorem there's a little sign in front. But you don't have to worry too much about this sign for the current talk. Oh yeah, and if the edges have multiplicity bigger than 1, what do you do? Well, you just take your graph and replace an edge of multiplicity m by m parallel copies, and then you take the trace now, and then you divide by m factorial. So that's not a big deal. Okay. Yeah. Yeah, we interpret we take a dual basis. Yeah, VW is the codeterminant with a dual basis. So you can contract them. Maybe in this, okay, never mind. All right, let's not go through that. Here, let's just do the square ice example. If you remember, right, so there's all the white vertices, the oxygens have degree 2, the hydrogens have degree 1, and therefore on each edge here, going from black to white, I've got a 2x1 matrix. So here's the matrices C1, D1, and so on, and there's a cilium somewhere. Then the trace of which determines the weight of the multi-web, well, the trace is the product over all the molecules, but in this case, the trace of this particular molecule just becomes the determinant of that 2x2 matrix, where I start with this column. I start with this column, and then that's the first column, and that's the second column. So the molecule, there's sort of 6 different possible molecules. Each one corresponds to a minor of this 2x4 matrix, which you make from the different columns there. Starting from the cilium, I go counterclockwise, C1, D1, C2, D2, and so on. I get a 2x4 matrix, and each molecule is going to be a Plücker coordinate that is a maximal minor determinant of this 2x6 matrix, of 2x4 matrix. And in particular, all the traces are going to be positive if the matrix itself happens to be in the totally positive Grassmannian, GR24. So this is, if you want to have a square ice model where all the traces are positive numbers, so that you can do probability, it's important to choose the matrices so that around each vertex, the 2x4 matrix is in the positive Grassmannian. Then all configurations have positive weight, and therefore you can do probability. And this turns out to be the same as the free fermionic point of the subvariety of the weights of the 6-vertex model, but more general. And yeah, so you can do play the same game with the triangular ice, but now the Grassmannian is GR36, which right. For every Grassmannian, there's this notion of what it means to have a totally positive Grassmannian, which just means all the Plucker coordinates, all the maximal minors are positive, or at least non-negative, that we care about. Does that make sense? In particular, in the positive GR36 Grassmannian, there's a special point of maximal symmetry with 6 or 12-fold symmetry, dihedral 6-fold symmetry, and that gives weights proportional to 1, 2, and 3 for the 3 types of molecules here. If the 3 edges are sort of adjacent to each other, it has weight 1. This one has weight 2. That one has weight 3, and gives a nice positive point in the Grassmannian, and therefore gives a nice positive probability measure on configurations of the 20-vertex model, which is particularly symmetric. Here. Okay, and there's a version for non-bipartite graphs. Maybe I won't spend any time on that just because I don't want to go over here. You can ask me later. Yeah, Castellan's theorem applies to non-bipartite graphs as well, and there's a version of the higher rank one as well, which uses symplectic matrices, I should say. Okay, but let me go on to the applications, unless there are any questions. Right, now you understand all the ingredients of the theorem, right? There's a certain Castellan matrix whose determinant counts the traces of multiwebs, and I think you know all the ingredients.
The code determinant for the non-bipartite one to think about what is the case.
Yeah, it's defined the same way. It's just but you have to use you pretend like, it's just that you use Pfaffians, yeah, it's a Pfaffian. No, it's still a codeterminant at each vertex, but then you have to take, when you contract it becomes a Pfaffian, yeah. Anyway, so here's a nice app. Let's go back to an SL2 connection. So all the vertices now have multiplicity 2. This is what you get when you take 2 dimer covers and just draw them on top of each other. This was one of the original applications we had in mind. Here I took a green and a blue dimer cover and drew them on top of each other, but you should sort of forget the colors, right? So just think of it as this is a 2 multi-web. It's just a covering of the graph where every vertex has degree 2. And this is the case where if you take an SL2 connection, so all the matrices are in SL2, then the trace of this multi-web, which is now this collection of loops, is the actual the product of the matrix traces of the monodromies of the connection around the loop. So you take to compute the trace of the multi-web, you take the product over all the loops, and each loop has you can just compose the 2x2 matrices around the loop. You get a 2x2 matrix. You take its matrix trace. I should have used a different notation here. This is the matrix trace of the monodromy, and it doesn't matter what order, whether you go clockwise or counterclockwise, because in SL2, the trace and the trace of the inverse are the same.
Is there a similar formula in general?
No. Yeah, because right, if you remember that if I take 3 dimer covers and superimpose them, I don't get a bunch of components. I get some web, which So there's not a simple, there's no analogous formula for SL3. Yes?
Can you tamper around with that too?
This too? Yeah, of course. This is just for the identity connection. If I put the identity connection, then all the monodromies are 2. But if I don't put the identity connection, I can have quite arbitrary traces of monodromies.
And would they have something to do with informing SL2?
No. Oh, if you want to make a quantum deformation, then this is not the technology you want. Right? We're staying in the free fermionic world here. Sorry, it's a little late for the question. No, the question was, can we deform SL2 to make a sort of put quantum weights or something, put a Q in there, and the answer is no, because everything I'm talking about is sort of free fermionic at the moment. But here's what you can do. Here's how you can apply this technology to give you something non-trivial. Let's put some punctures in the surface, like at some faces, and then ask the question, can we detect, what's the probability that our multi-web, when we superimpose these 2 dimer covers, has some particular isotopy, some loops in a particular isotopy class in the complements of the punctures, right? What's the probability that there's a loop which goes around these 2 punctures but not that one, for example? Right? This is some sort of large-scale observable, which we can now, in principle, detect with this technology. That's what I want to explain. So what we can do is take a flat SL2 connection, right? What does flat mean? It just means it has trivial monodromy around all the contractible faces, not the ones with a puncture, but all the other faces. In that case, the trace now of a configuration is 2 to the number of loops, but then for every non-contractible loop, every loop which surrounds 1 or more punctures, I won't get the identity map, it'll get the trace of the monodromy. Well, it's 1/2 because I put already 2 for the number of loops, but then you get this extra variable that you can play with, which is the monodromy around those punctures. So essentially the trace, the multi-web trace can be used to detect the homotopy type of the loops because we have these extra variables to play with. And
so in a sense, this. No,
yes? Go ahead.
Those 2 becomes 2 cosine of sum over theta j's, where thetas are some parameters.
Exactly. Yeah.
Associated to the stars.
Yeah. They don't have to be unitary, but yes, that's right.
Well.
Fine. Okay, so basically our determinant, which is now a sum of traces of multiwebs, if 2 multiwebs have the same homotopy type in the complement of the loops, then they contribute the same trace. And so we can just group things according to their different isotopy classes of closed loops in the complement of those punctures. Right, so what we do is we just take this sum and group the configurations according to their isotopy classes in the complement of the punctures, and therefore we can write our determinant as a sum of some integers, c lambda, times the trace of lambda, where lambda runs over all possible simple closed curve systems in the complements of the punctures. And so now we can ask, we have some new sort of probability measure on the simple closed curve systems where these coefficients are just the relative probabilities. And there's a theorem of Falk and Goncharov which says that these trace functions, as you let the connection vary over all flat connections, these trace functions are a basis for the linear space of regular functions on the set of all connections, flat connections. So in principle, since these functions are a basis, we can figure out, but just by linear algebra, you can compute the coefficients. So the coefficients are determined, and of course we don't. Well, not of course, but it turns out to be kind of a hard problem to extract the coefficients from such an expression, because there's some sort of infinite dimensional linear algebra which we don't really understand how to do in general. Yes?
And do you expect that it is possible in general? I mean, okay, do you expect that you can extract C lambda from the knowledge for any?
Yes, yes.
Yes.
I think we're just missing we need to find the correct definition of dual basis. Once we find the correct definition of dual basis, we could just apply it to this, to the determinant, and we'll pick out the coefficient. But here's a case where, in some cases we can do it. I mean, certainly if the graph is finite, it's a finite linear algebra calculation, we can do it. But the interesting case is when to sort of understand it in the scaling limit. So here's a scaling limit calculation for a very simple surface, which is an annulus, or if you like a surface with just a single puncture. In the appropriate, if you let the mesh go to 0 for the double dimer model, you can ask how many curves go around the annulus. How many curves in how many double dimer curves have are topologically non-trivial? And the answer is kind of very, very, very pretty. If you make a generating function for the probability that there are j curves times u to the j, sum over j, then there's a nice product formula on the right-hand side.
So as they look like Chebyshev polynomial, Philippe will do that ultimately.
That's right. Philippe could have done this in his sleep, apparently, because there are Chebyshev polynomials in the background. Sergey.
Can this also be done on a surface of higher genus?
We don't know how to do it on the surface of higher genus. I mean, in principle, it can be done, but there's a couple complicated things in the way. First of all, we don't know a dual basis, so we don't know, there's some mysterious integral we have to do to extract these. Now, we don't know how to compute the left-hand side very well. Now, you need to get a pretty good expression for the left-hand side, the determinant of this Castellan matrix, which you can do for an annulus, because the annulus has this symmetry. But for a higher genus surface, that's harder. Or even for a planar domain with multiple punctures, this becomes a hard problem. Okay, so how much time do I have left? We started, what? 5 minutes, okay, great. That should be enough. What do we do with n equals 3? Here's my second, oops. You take 3 dimer covers, you superimpose them, you don't see any internal structure. Where do we, what kind of observable should we be looking at? Well, it turns out that there's still some internal structure. Secretly, there's a spine, sort of a spine. If you have a colored 3 multi-web like this, there's a sort of something called a reduced web inside it, which somehow connects the boundary points. The issue with this is, and I'll tell you how to find that spine. The problem is that the spine is not sort of canonical. It depends on some order in which you reduce the web. But the topological type, the way it connects the boundary points together, is canonical. So there is still something left to observe, which is the topological type of the boundary connections, even though the actual blue curve here might not be canonical itself. So how does it work? Well, first of all, once you have this 3 multi-web inside your graph, there's sort of an abstraction of it, which is called a web, a 3-web, which is a trivalent graph, possibly with some floating cycles. Well, you do this sort of obvious thing. There's some trivalent vertices over here, which become vertices over here, and then there's a path, which consists of edges of multiplicity 1, 2, 1, 2, and so on, which connect them. And you throw away the vertices, the edges of multiplicity 3. So from the multi-web, you get this sort of abstract graph, trivalent graph, and then you do certain reductions, which I guess I should tell you those first. There's a certain sort of set of web reductions or skein relations for SL3, which are, every floating component, every loop here gets multiplicity 3. Every bygone, you can remove it and multiply the resulting web by 2. And if you see a face of degree 4, you can replace it with either this web or that. And those reductions act on the linear space of linear combinations of webs, but they preserve the trace. And so given some potentially complicated 3 multi-web, you can do these reduction rules to replace it with a linear combination of reduced webs. What is a reduced web? wait a minute, did I forget to tell you what a reduced web is? I forgot to tell you what a reduced web was, but a reduced web is one where there are no faces of degree 0, 2, or 4. If you have a face of degree 0, like this, or 2, or 4, you can replace it with a linear combination of webs with fewer faces. So reduced webs are those which have only faces of degree 6 or more, and the resulting theorem, just following what we did in the SL2 case, is that the determinant, now you can group webs according to the isotopy classes of reduced webs. And because the trace, one can show, because the skein relations preserve the trace only depends on the isotopy, on the reduced web itself. But again, you can ask how do we get these coefficients? And again, there's the same problem. We don't know if there's a dual basis for which we can extract these coefficients. But in principle, you can do that, and we did it for the annulus. Again, on an annulus, every reduced web is again a union of loops going around the annulus, except here there's kind of two different kinds of loops. There's the ones which go, starting from a black vertex clockwise, they go 1, 2, 1, 2, or the ones that go 2, 1, 2, 1. So you can think of those as two different orientations. And again, there's some nice formula for when you make a generating function in the scaling limit, on the scaling limit of the annulus, where Q is the conformal modulus. If you look at a generating function for the number of configurations which have I loops going of one type and J of the other type, it again has a nice product formula.
When you have defect on the boundary, do you have some control over how many reduced webs there are?
Yeah, that's for the next slide. So just like in my picture here, right, there was some boundary sort of insertions there, and the internal web in this case has like 6 different possible topologies. And again, in this case, one can do the coefficient extraction, and in the scaling limit. So if your surface has no topology, if it's just simply connected, if it's just a disk with some boundary points, you can do all the calculations. And in the scaling limit, you get some kind of pretty formulas like this one for the probability that your reduced web has this topological type. This is one of the 6 different topological types of reduced webs when you have 6 boundary points, which are white, black, white, black, white, black. And here's sort of what that spine might look like in this case. It's kind of got a hexagon and then 6 arms coming out to the 6 different boundary points. And you can show that this is indeed some sort of conformally invariant quantity, connection probability. I illustrated it on the upper half plane, but it works, on any domain through some conformal invariance properties. Okay, I think I'm.
Positions of the tripod points are non-canonical because only the topology.
Right, only the topology is conformally invariant. The internal structure, we don't know how to make that conformally invariant right now. I mean, there may be some sneaky way to do it, but there's nothing obvious. Mm-hmm. Thank you, and happy birthday.
Okay, thank you. Are there any more questions?
Is there any hope of doing a theory of limit shapes of those objects?
Yes. Right. If I can take it just a second here, the reason this formula is nice and just a product, I mean, factorizes completely. I mean, if I took some more complicated topology here, there would be some big polynomial, big rational function. This one factors nicely, and there's a whole multi-parameter family of configurations which factor nicely for some reason. It's like some SL3 version of Gessel-Vienot. And if you move these points around, the expressions, you can look at how the probabilities change as you move the points around. And so, you know, if you try to squish points over here and rarefy the points over there, you can see that there's some sort of local entropic repulsion going on, and from there you can make limit shapes. But, you know, what we're missing is how to figure out what in order to understand that, you need to know what the internal structure is, and we don't know what that looks like. So.
Any other questions? Andrea.
A short one, maybe on the same topic. Are we really 100% sure that the only thing which is invariant is the topology, and there is nothing else like the...
No, absolutely not sure. Absolutely not sure. I think there is a way to figure out what's going on here. And I can tell you how I made this picture. I tried to do it in a conformally. I cheated a little bit, but there's a sort of... How you make this picture is that, you know, you have to take this triple dimer cover and then do some reductions. And the answer depends on the order in which you do those reductions. But if you do the order, if you sort of point your finger at various locations according to some sort of Poisson process, then, or maybe Poisson process, hyperbolic Poisson process, then you can show that the result in principle is conformally invariant. I mean, one might hope to show that the result is in principle conformally invariant. Right? The problem is that it doesn't commute. If you do a reduction over here and over there, the order matters. You can show that the order matters, but it's possible that if you do a random order, then the result will still be a conformally invariant object. Yes, Sergey?
Do you think that these paths that you get here, like in the scaling limit, they will be some kind of SLE with some parameter that you can maybe guess from some physics voodoo?
Yeah, that's what we thought originally, but they're not consistent with any SLE. For one thing, the central charge is supposed to be 2, which doesn't correspond to any SLE. So the current understanding is that there's some new kind of object.
Which is still conformally invariant.
Yeah. But it doesn't have the same, it doesn't have the like domain Markov property that SLE does, so you wouldn't necessarily expect it to be SLE. No, don't throw it too hard.
Okay, let's thanks Rick again and move to the end.